Guys, today we're on Unit 10, Lesson 6, and we're going to be discussing limits and continuity. So we're going to start today's lesson. We're going to use the graph below to complete the table with the given information. After filling in the table, we should be able to write the three pieces of information that must be true in order for a function to be continuous at x equals c. Okay, so we're going to worry about filling out this in just a few minutes. And we're going to have to kind of do a little bit of working with this table. Okay, so first of all, if we look at the table below, x equals c. Okay, so in that left column there, we're going to evaluate, we're going to cross off x equals 9. I'm not going to worry about that one. So when x equals 4, first we want to find the function value, meaning what do I get when I plug in 4? So if I go to 4 on the graph of my function and I plug in 4, it's undefined. Remember, when you have an asymptote in your graph, it's undefined. So f of 4 is undefined. Find the left-hand limit. So I want to do the limit as x approaches 4 from the left. So I'm going to go to 4 from the left. And there is no answer, because if you notice, my graph ends at 3, then I'm skipping a little section here. That's a little tricky, but the limit does not exist because there's no graph there. Find the limit as x approaches 4 from the right. Okay, so maybe I should write that down. This is what we're actually doing. I should have written it down in the other box. So the limit as x approaches 4 from the right. Now this time, if I go up to my function, I notice my arrow is heading towards positive infinity. So this limit is positive infinity. Find the general limit. In other words, we want to find the limit as x approaches 4. Well, remember, when we want to find the general limit, then we go to either side. We can do it from our table and compare that, or we can just look at the graph and see that the limit does not exist. Is f of x continuous at x equals c? Remember what it means to be continuous. A continuous function is no holes, breaks, or gaps. When x equals 4, we have everything going on there, right? We have a big gap in that function. So this function is not continuous. Let's look when x equals 3. So now I'm going to kind of go here on the graph of my function. F of 3. When I plug in 3, what do I get as my answer? So when I plug in 3, I get, oh, sorry. I forgot that I had some bad questions here. We want to -3. We're going to analyze -3. I'm sorry about that. So f of -3. So I'm looking over here on my graph. And some of you may find it helpful to kind of, if you want to draw like a little vertical line there, that's what we're analyzing. So when I plug in -3, my answer is -6. The dot is your answer. Now let's analyze the limit as x approaches -3 from the left of our given function. Go up to your picture, -3. When I go to the left side of -3, my y values are getting closer to 5. What happens when we evaluate the limit as x approaches -3 from the right of our function? When I go to the right of -3, my y values once again are getting closer to 5. So what is the limit as x approaches -3? Well, since my left limit and my right limit are the same, right? Since I'm approaching the same number, remember that missing point there, that does not matter. Your y values matter. My limit is 5. Is this function continuous? Remember, continuous means I can just move through the point without lifting up my pencil. No, I have to lift up my pencil, go down there, and then go back up to the graph. So this function is not continuous. Now let's look when x equals 0. F of 0 equals. When I plug in 0, I get 6. The limit as x approaches 0 from the left of my given function. If I look to the left side, and again, if you want to maybe draw a vertical line, if that's distracting, then get rid of it. As x approaches 0 from the left, my y values are going to 6. The limit as x approaches 0 from the right of my function my y values again are going to 6. What is the general limit? Now remember, we consider both directions. You could do it by looking at the graph. You could do it by looking at the numbers you got here. If they're the same, the answer is 6. Is this function continuous at C? Visually, when I pass through 0, right, when I plug in 0, can I draw that portion of the graph without lifting up a pencil? Absolutely. So yes, this function is continuous at C. What do you notice? In order for a function to be continuous, right, our limit and our function value are the same numbers. So our 3-point conditions are 3 things that have to happen. When I plug in a number, I have to get an answer. When I evaluate a limit, I have to get an answer. And most importantly, the limit has to equal the function value. So those are the 3 conditions that have to exist. So now, without breaking it down, let's look at this next little piece here. Is f of x continuous at x equals -5? So now what do we have to do? I'm going to evaluate -5. F of -5 is -2. I'm going to evaluate the limit as x approaches -5. Now, when I evaluate the limit, notice what's happening on your graph. Now, we could do it right visually from the graph if we want. At -5, what do you see here? My left limit does not match my right limit, right? I have a big space here. So my limit does not exist. Is this function continuous? Obviously not, right? We see this big jump right there on our graph. No. Why? Well, which one of our rules failed? I get a function value, but I did not get a limit. Okay. So when we move through these problems, okay, again, when we move through these problems, we're going to always have to like kind of consider what we're dealing with. So just want to remind you, a continuous function has no holes, breaks, or graphs. So types of continuous functions, obviously linear, will be continuous for all x values. Polynomials, again, always continuous. Exponentials, continuous on their domain, right? Radicals, continuous on their domain. Absolute value. And our sine and our cosine. Okay, so these are the functions that you may see. Types of functions that are going to be discontinuous. Rationals and piecewise are going to be the main functions we're dealing with in this class. So before we move on, let's just kind of talk about a little bit more about discontinuities and how we describe them in a calculus class. So one type of discontinuity is called removable or point. Okay. So in this case here, if I'm looking at this function, it's not continuous when x equals 1, but it's just not continuous at this point. And basically, it's removable because we could redefine the function. And again, that's going to be stuff we're going to do next year. This year, we just want to kind of be able to describe it. Non-removable is when you either have a jump or an asymptote, or at least one limit exists, but the other doesn't. Okay. So again, not the biggest deal. I want to remind you, I'm pretty much just introducing these words. I'm more focused on you being able to kind of see things in the picture at this point. In this next set of examples, let's just identify whether or not the function is continuous or not at the specific value, and then justify your answer with a 3-point definition. So at x equals 1, is this function continuous? No. And if I look here, I have a function value, but what's the matter? I don't get a limit. So it's not continuous because the limit as x approaches 1 does not exist. If you had to describe this as a removable or non-removable, which example, which column does this fit in? This is going to be a non-removable. In our next example, when x equals 1, is this function continuous? I have a limit, but I don't have a function value. When I plug in 1, I don't know. Because f of 1 is undefined. This is called a removable, right? This fits this category over here. And in my last example, when I look at 1, when I plug in 1, I get an answer. When I evaluate the limit, I get an answer. All 3 of those answers match. So at x equals 1, yes, this function is continuous. And the reason being, because the limit as x approaches 1 is the same value that I get when I plug in 1. Okay. It's pretty easy to see continuity on the graph of a function, because if you just think about not lifting up your pencil, it's easy to deal with. When we're dealing with algebraic situations, it sometimes gets a little bit trickier. So I just want to remind you, whenever we evaluate, we're going to always plug in a number. We want to get an answer. Evaluate the limit. And then compare. Whenever when the first thing fails, you're done. As soon as something fails, your function is not continuous. So always start by plugging in the number. If I want to see if this function is continuous, I'm going to evaluate -6. Undefined. Already done. Since I don't get an answer, it's not continuous at c equals -6. Not going to be so concerned about you justifying at this point. I just want you knowing the steps of what to do. In example 2, I'm dealing with a piecewise function. So I want to figure out if this function is continuous at c equals 0. I'm going to start by plugging in 0. When I plug in 0, I get 1 as my answer. Now I have to evaluate the limit as x approaches 0 of the given function. So we have to think about, how do I evaluate this limit? Go up to your piecewise function and think about what's going on. When I plug in the number, I get 1. That I already did. When I go to evaluate the limit, I'm going to use this function from the left. Same function. X squared minus 6 over x plus 6 when I'm plugging in numbers from the right. So I'm evaluating one-sided limits, but I'm using the same function. Okay. So I can just do it in one step. So I'm going to evaluate x squared minus 6 over x squared plus 6. 0 squared minus 6, 0 squared plus 6. I get -6 over 6, which is -1. Plug in a number, get an answer. Evaluate the limit, get an answer. Do those two numbers match? Since they're not equal to each other, right, this function is not continuous. Maybe I will justify this time. Not continuous. And the reason being, the limit as x approaches 0 does not equal f of 0. Oh, now we have a crazy looking piecewise function. Break it down. If I want to test whether or not it's continuous at x equals 0, right? I'm testing at that point, at that jump, without having to sketch the function. I start by plugging in 0. What is f of 0? When I plug in 0, I'm going to use this rule. When I plug in 0, I get 0 for my answer. Now I want to evaluate the limit as x approaches 0. So I want to think about, how do I evaluate this piecewise? And my two main pieces right now are 0 and 2, right? When I'm less than 0, I'm plugging into x squared. When I'm greater than 0 but less than 2, I'm plugging into x plus 1. And when I'm in between 2 and 5, I'm plugging into 5 minus x. At this point here, we're just concerned was 0. So if I go to evaluate the limit as x approaches 0 of this given function, I see I have to break it into 2 pieces. I need to evaluate a left limit and a right limit because my function behaves differently from either direction. So I'm going to use that rule and I'm going to use that rule. The limit as x approaches 0 of 0 squared is just 0. If I plug 0 down here, I get 1. What do you notice about these two numbers? They're not equal, so this limit does not exist. Plug in a number, I got an answer. I evaluate the limit, I did not get an answer. So no, not continuous at x equals 0 or c equals 0. And if you had to explain why, because the limit as x approaches 0 does not exist. Let's look at c equals 2 of this given function. Start by plugging in your number. F of 2. What rule am I going to use? So now we're looking here. Right now we're looking here. When I plug in 2, I'm going to use the bottom rule. 5 minus 2 equals 3. So when I plug in my number, I get an answer. Now I need to evaluate my limit. My limit as x approaches 2. When I go up to my function to see what to do, it's a piecewise function, so I need to break it up. Limit as x approaches 2 from the left, the limit as x approaches 2 from the right. What rule am I going to use when my numbers are less than? I'm using x plus 1. What rule am I going to use when my numbers are greater than? I'm plugging 2 into 5 minus x. 2 plus 1 is 3. 5 minus 2 is 3. My overall limit is going to be 3 because these numbers are the same. Plug in a number, get an answer. Evaluate the limit, get an answer. If the answers match, yes, f of x is continuous. At c equals 3. Because, and remember, I'm not going to get so technical, but I'd like you to see this. F of 2 equals the limit as x approaches 2 of our given function. Okay, so that's a little bit of continuity. We're going to discuss this again tomorrow. Practice your homework questions, and we will see each other soon.